In this paper, we present an algorithm to solve trajectory retiming problems for not only the time-optimal objective, but also for quadratic objective functions. First, let's give a quick introduction to the retiming problem. In this problem, we're given a path q, and we're trying to find the optimal function s of t, which describes where along the path we should be at time t, to satisfy some constraints and objectives. This is useful when it's easier to first compute a viable path, followed by an optimal feasible speed profile, as opposed to computing the entire trajectory as a single optimization problem. For example, machining, painting, and welding are examples of problems where the path generation problem is almost completely decoupled from the trajectory timing computation. In fact, any problem that doesn't strictly require joint kino-dynamic motion planning can be separated into path generation and trajectory timing components. Trajectory retiming could also be used for problems that are one-dimensional, such as computing the optimal altitude versus time profile of an ascending rocket through various atmospheric conditions. The time-optimal trajectory is by far the most common retiming objective, where the cost function is to minimize the total duration of the trajectory. Another way to state this is that we want to go as fast as possible without violating any limits or laws of physics. But this is often suboptimal because it constantly drives controls as hard as it can. As a simple example of a situation where this is undesirable, consider a machine shop. If we naively maximize production rate, we're going to wear down the tools much more quickly. Instead, we should have some cost associated with machine time and some other cost associated with how aggressively we machine. As another example where this is undesirable, consider that operating at the control limits will leave no margin for a closed-loop controller to correct against any disturbances. We demonstrate this example later in the video. One approach to solve this issue could be to reduce the control and/or state limits to build in some safety margin, but tuning this might be finicky because too much margin might cause infeasibility, while too little margin causes lack of stability. Using our proposed algorithm, you can solve the retiming problem with not only the time-optimal objective, but also with general quadratic objectives. In this example, we set up a cable-driven parallel robot problem with tension limits. In the time-optimal solution on the left, the cables frequently saturate the tension limits, which results in times when the closed-loop controller loses controllability. If, instead, we use the quadratic objective shown on the right, the closed-loop controller will have much more margin to work with. To describe our approach, let's first define the retiming optimization problem we want to solve. We want to handle general quadratic objectives with possibly time-varying coefficients, subject to standard second-order dynamics and joint state control limits. We then apply the standard parameterization for retiming, discretize, and do some algebra to turn our second-order vector-valued variational calculus optimization problem into a sparse QP problem with scalar variables. We could, of course, use a generic QP solver, but we show in this work that the structure of this particular QP also enables an extremely fast linear time algorithm. Specifically, the way we do this is to solve for one variable at a time. In general, this would result in an exponential time algorithm, but when we visualize the structure using a factor graph, it becomes clear that we'll never need to solve anything larger than a two-variable scalar QP, which can be done in constant time. And since we have O of n total variables, we can solve the quadratic objective retiming problem in linear time. Now I want to very carefully emphasize that exact variable elimination with inequality constraints normally has exponential complexity, but the main takeaway from this paper should be that for this particular problem structure, it's actually linear complexity, and graphically depicting it as a factor graph form can help identify what complexity variable elimination will have for a given problem. So stepping through the elimination, we first eliminate u0. Because there's an equality constraint on u0, this is trivial and just amounts to substituting the expression for u0 in terms of x0 and x1. Next, we eliminate x0. At this point, x0 shares factors with only one other variable, which is x1, so we'll need to solve a parametric QP of two scalar variables, but this is relatively easy to solve. We can proceed to eliminate the rest of the variables in much the same way. Walking through the variable elimination in this way, we see that the hardest thing we'll ever have to do is solve a two-variable parametric QP. Although we don't have the time to show the full details, let's try to get an intuitive idea for what one of these parametric QP elimination steps looks like. In this example two-variable problem, we have a quadratic objective which is optimal when y equals x, and we have a diamond-shaped feasible region. To solve for or eliminate y, we first solve the QP parametrically for y in terms of x, which generates a piecewise linear solution. And then we substitute the solution back into the original problem to create a new piecewise quadratic program that doesn't involve y. Noticeably, the parametric solution to a two-variable piecewise QP is easy to solve and always piecewise linear. Similarly, substituting a piecewise linear equation into a piecewise QP always generates another piecewise QP. Although in theory the number of segments in the piecewise expressions may grow, we find that in practice for many robotics retiming tasks it does not. Of course, pruning can always be done to trade global optimality for speed if desired. So summarizing, first, we express our problem as a quadratic objective retiming problem. Then, we reparameterize and discretize to obtain a sparse QP. And finally, we eliminate one variable at a time to solve the sparse QP. The result is an efficient algorithm to solve our retiming problem, in which we may have joint state action constraints and multiple quadratic objectives we seek to balance.
Here you can see our experimental setup of a planar cable-driven parallel robot. The end effector is the white square with black outline, and the 4 cables are highlighted in blue. In this video, the robot traces out the star shape using the time-optimal parameterization. We can observe 2 things. First, the end effector shakes and bounces quite a bit. Second, the end effector deviates from the nominal path, especially at the top left of the star. It's a little bit difficult to see, so let's annotate the video with motion trails. Notice here on the 3rd vertex of the star how the robot doesn't decelerate fast enough and carries extra upward velocity into the next edge. To understand what's happening, let's take a look at the nominal cable tensions. Now on this robot, I happen to know that the bottom right cable, which is cable 1 in black, has some extra friction in the system. If we observe the plot on the top left very carefully, which is the time-optimal parameterization, we can see that at the third vertex, cable 1 is asked to pull with the maximum allowable tension. Due to friction, it can't quite achieve this full tension. Furthermore, its primary antagonist cable, which is cable 3 in green, is at the minimum allowable tension, so it cannot loosen up anymore to help decelerate the end effector. As a result, the end effector is unable to fully arrest its motion and continues with an upward trajectory on the following edge. Contrast with this with the quadratic objective solution on the right, which balances both the speed and the margins to the tension limits. As a result, all the cables have plenty of margin for the closed-loop controller to compensate for friction and other non-ideologies. Now we show the video of the solution with quadratic objectives and with motion trails. Finally, here's the 2 trajectories side by side and with motion trails. Thank you for your time, and feel free to check out our code linked in the paper.